Morning, everybody, and thank you very much for that wonderful introduction, which I hope I can live up to. And just want to say that I'm not growing the LCT community by myself by any manner of means, and that the conference in 2015 wasn't only my doing. We had Carl, Sue McKenna, who's here, and Sue Ellen Shea, who unfortunately cannot be here due to illness. But the four of us met regularly on Skype, and I think Carl and Sue Ellen did the bulk of the academic work in terms of reading the abstracts, etc. So I feel quite embarrassed at taking credit for all of that. But thank you, and also want to say thank you to Carl for inviting me to make this keynote address. Carl, as everyone here knows, is one of the most generous academics that I've ever met, and I'm sure that most of you have ever met, who's not only kind enough to invite me to do this, but is kind enough to all of us to allow us to watch this field growing, to see a theoretical framework developing, and to make whatever small contribution to it we all can. So thank you for your generosity, Carl. Okay, the title of my talk, the South Africans here will recognize the oblique reference to changing the higher education landscape, which was the role of the first higher education minister in the first democratically elected government in South Africa. And as many of you probably know, the South African higher education system under apartheid was a very segregated and divisive one, where some universities had access to resources and others didn't, and universities were separated along racial lines. So there was clearly a need to do something about this situation, and the solution that arose, which I suppose made some sense at the time, although had unintended consequences, was to merge institutions, particularly historically disadvantaged with historically advantaged universities, to attempt to change the landscape and to normalize the South African higher education landscape. 3 divisions of universities were also created at the time, which were traditional universities, some of them research intensive, not all of them research intensive. Comprehensive universities, which was the combination of a traditional university and what we used to call technicons, which were kind of equivalent, I think, to the British polytechnics. And then the technicons, the polytechnics, had a kind of a magic wand waved over them and told you are now universities. They weren't. They were very definitely not universities before, but by legal decree they became universities. So this was the kind of landscape that happened in South Africa soon after the first democratic elections in 1994. And I think universities of technology are still struggling to kind of find their identity and to say, what they are. They sort of knew what they were when they were technicons, and really struggling to understand what their role is in the new kind of 3-layered differentiated higher education system. So unfortunately, the minister, while rightly wanting to change the size and shape of the landscape, he didn't pay any attention to its knowledge-scape. And there are clearly intended to be significant differences between the kinds of programs offered by universities of technology and traditional universities in South Africa and elsewhere. And universities of technology like mine have traditionally had strong links with worlds of practice, with industry, agriculture, hospitals, community development. And they built their traditional knowledge base on these links with practice. And the process of redesigning South Africa's higher education system has inevitably been one that has not valued the practice base of the universities of technology, with unfortunate educational and economic consequences. So what I'm hoping to do in this talk is to, the talk has got three main sections. I'm going to introduce you to the problem about the knowledge scape, and how where we are in trying to think about the knowledge base of vocational, technical, and professional higher education, particularly of the kind offered by universities of technology. And then I'm going to, Carl has kindly given me the opportunity to showcase some of the work that we are doing in my research unit, which I've called Opening the Black Box of Practical Knowledge, one LCT case study at a time. And then hope to make an argument around a reconceptualization of the knowledge scape of South African universities of technology, with the help of LCT tools. And in doing this, as I said, I'll be drawing on the work of colleagues and some of our postgraduate researchers in our work integrated learning research unit. And although my focus is very much on our own universities of technology, I hope that the insights provided by the LCT tools will have some relevance for others as well, dealing with vocational and professional education. Okay, so yesterday Carl introduced us to some of the big dualisms, the big divides. Here's the little cluster of the ones that I'm dealing with, and of course there are many others that we can add to this. And there are a number of such disabling dualisms about the purpose of higher education, based on an understanding that there are these absolute distinctions between academic and vocational education. And this, of course, translates into these binaries of theory, practice, academic, vocational, education for its own sake and for growth and development of the individual versus education for employability, heads and hands, broad versus narrow, conceptual and contextual, etc. There are many others. So this binary is real in the sense that it has generative power. Theory and not practical usefulness counts in the academy, and in vocational higher education, we want to ensure that practical usefulness and competence is valued. But we don't want technical education to be atheoretical, and there's quite a lot of bad vocational education around, and probably quite a lot of bad traditional higher education too. But strong vocational education, such as might be found in the technical universities of Scandinavia, Switzerland, Germany, and Netherlands, is quite powerful stuff. It's neither weak, narrow, nor anti-intellectual. So what I'm suggesting here is that understanding something of these boundaries, which also includes understanding and respecting the integrity, coherence, and purposes of some of these differences, is important. And that we need to understand the underpinnings of these binaries and their competing claims to legitimacy in education. And if we understand these without necessarily destroying the boundaries, although I think blurring them a little bit is very useful, and perhaps putting them on a plane, on a Cartesian plane, is also kind of useful, because there is a lot of movement and transfer across them in most forms of good education. But I think what we really want to do is to construct some pathways, and pathways that can help us to navigate beyond these binaries and their polarized discourses. So, I'm going to mainly be using the semantics to explain, to use semantics as an explanatory tool to understand some of the operational, the mechanisms below the binaries, and I've highlighted some of the case studies and the work done in the center that make use of semantics. Otherwise, as everyone knows, we'll be here all day if we go through all the tools. So most of our qualifications sit in this rather difficult space on the semantic plane, kind of straddling that prosaic and worldly zone, with some qualifications much more clearly located in one or other of the zones, depending a lot on the history of the qualification and where it came from. Some of the qualifications came very much from a very vocational field, such as secretarial studies, and others came from a field which sits more comfortably in the worldly plane, such as engineering. So, this is the definition of a diploma. Now, the diploma is a very key qualification for universities of technology. This is a definition from the South African Council on Higher Education, which understands that the diploma has a different kind of knowledge base from a degree. It includes professional, vocational, and industry-specific knowledge, and that is, and what the qualification is for is really to enable graduates to use this focused knowledge in a particular field. And they also go on to say that it's that probably gaining experience, work-based learning is a kind of a signature pedagogy of the diploma. So as a definition, it's okay-ish, if rather vague, but not particularly useful as a guide to helping the universities of technology to develop diploma curricula. And this is not much, there's not much more than this that the Council on Higher Education provided us with, just a little more technical detail about how many credits, etc., are required. I think this is a kind of a pivotal moment for universities of technology, because basically it shows that what they do can't really be described terribly well, and it's such a key qualification for higher education transformation. Students can come into a diploma with it has a much lower entrance requirement. So the minute you put a degree requirement on, it ups the game quite a lot, and it excludes many students from higher education studies or from any kinds of studies that would enable them to increase their life opportunities and to find meaningful work post-graduation. So it's a huge pity that more attention wasn't paid to this crucial qualification, which I think would mean a lot for, if it was better understood, would mean a lot for inclusivity and for transformation of the South African higher education system. So this is the kind of qualification I think that we would describe as a high in semantic gravity, SG plus and SD minus or plus, depending on the kind of on where this qualification would lie on the prosaic to worldly continuum. So we know quite a lot about theoretical knowledge. It's been studied and scrutinized quite a bit. And we know that theoretical knowledge is not the same kinds of theoretical knowledge in different disciplines and fields, but it has some common characteristics. For example, it is verifiable, at least in some sense. It's accurate or able to be supported. And this characteristic might seem obvious, but we do need to remind ourselves of this at a time when the scientists have to take to the streets to defend the science of global warming. It has explanatory power. Theoretical concepts explain natural and social phenomena. It's generalizable. It travels across contexts because it functions in the realm of concepts and abstract propositions. It's analytic, so while it's independent of particular contexts, you can use it as a tool to analyze problems in their contexts. It's integrative and synthesizes new and prior knowledge, creating denser and more complex concepts and networks of concepts. And finally, it has predictive powers. Our theoretical understanding of, for example, an educational policy might help us to predict what could happen or couldn't happen within an educational system. So it's the kind of knowledge that we refer to as high in semantic density and low in semantic gravity. And as Carl repeatedly points out, it's located along a continuum of strengths because there are obvious differences in the complexity and depth of different concepts. Some have greater explanatory power, some have less, some integrate many concepts, some less, and so on. So this kind of knowledge, I think, has been studied quite a lot. However, practical knowledge is a bit of a black box. We know far less about practical knowledge. We know that it's not the same across disciplines and fields, but people do tend to refer to practical knowledge as if it was one thing, as if it was the same. And it's many, many things. I think it's part of the difficulty of finding a suitable name, because there are many names, such as situated knowledge, contextual knowledge, tacit knowledge, and practical knowledge has all of these elements to it. But it is what Gerardi calls docta ignorantia, the knowledge that doesn't know itself and can't very often, I don't think it's not able to describe itself, but very often it can't describe itself. And it seems to straddle quite a wide range of practices, from the craft of soldering, software technicians who solder circuit boards, to the advanced practices in medical imaging and even surgery. So there's an enormous range of practical knowledge. But there is hope, because there have been some very interesting studies that are opening up this black box, and some of them are being presented at this conference. So just a little bit of history of our unit. These are some photographs of the group of us who've been working in this field of trying to open up the black box, officially since 2002, when our centre was launched with a National Research Foundation grant. But before that, the centre grew out of a project led by Cecilia Jacobs, and there's a picture of all of us looking considerably younger. Some years ago, I think it was in about 1995 or so, that Cecilia got a US AID Foundation grant to look at communication practices in the disciplines. And the project consisted of 10 folks from these various vocational fields, and 10 other folks from applied linguistics. And we worked together with our disciplinary partner, trying to understand their practices. That's me in the hard hat. I don't know if you can see that. That's a hard hat on my head, which is quite prophetic, I think, considering my subsequent interest in engineering education. So from this kind of research group, we put together this proposal and started work trying working in different directions on vocational education and trying to understand some of its underlying mechanisms. Of course, we didn't have access to LCT back in those days, but we have been going at it for a while. We celebrated our 15th anniversary earlier this year, and many of us developed PhDs and published our first articles in this group. These are some of the knowledge resources that we used before LCT, and don't worry, I'm not going to go through all of them. You can see that obviously the main resources that we used, I recently did a kind of a literature review of some of our some of the practice, theories of practice that we've looked at over the past years, and came up with these kinds of clusters of categories that we had worked with, the kinds of authors and theorists that had guided a lot of our work. And we were particularly interested because I think of that original project where language lecturers were paired up with vocational lecturers. We kind of developed an interest in boundaries and boundary crossing, boundary objects and epistemic objects and transaction spaces, etc. And so we've always been in our group a little bit transgressive and have tried to explore things beyond the binaries. Okay. In more recent years, we've of course discovered LCT, and I first met Carl in around 2010 when Sue Ellen Shea invited me to a workshop. She had been working on the SANTED project, which was a project to try and look at the knowledge base of comprehensive universities, and I'd been using Bernstein to look at our qualifications, and was not to receive the sort of privileging of the theoretical was not particularly well received in the vocational context, as you might well imagine. So Sue Ellen invited me to this series of workshops that Carl was offering at UCT and said to me, "I think you might be interested in this guy." So, and indeed I was. I came to the workshops and suddenly from the binaries, it opened up into planes, and not only planes, but planes with kind of layers and nuances to them. So we started kind of exploring LCT, and that was, from about 2010, 2012. And eventually got up the courage to invite Carl to come over and do some workshops with us to work more with in the kind of vocational field, which he very kindly and generously did. So that was last year. Stellenbosch University and ourselves jointly hosted Carl, and I think Carl introduced the autonomy codes at that particular event. So we've been very privileged to be taken along this journey, and the LCT tools do seem to be working very effectively for us in trying to explain what this mysterious practical knowledge might be. So, and I must apologize for the boxes, Carl. I was trying to kind of get the colors of the conference, and on my computer it looked quite nice and fuzzy and not so boxy, and it's come out very boxy. So you just ignore the boxes and kind of think of it as a fuzzy thing. So, okay. This is our problem. It's the current problem for universities of technology is one of, well, there are many problems, but a knowledge problem is around academic drift and what to do about it. Academic drift has been caused by a sort of combination of legislation and aspiration. So it's become increasingly recognized that the diploma programs have suffered from academic drift. It's a problem not unique to South Africa. Many, I think, international universities, as they try to modernize their qualifications and put them on a more scientific basis, experience something similar. But in our case, I think the main reasons have to do with legislation. Legislation to standardize South African qualifications on the South African qualifications, national qualifications framework invalidated almost all of the University of Technology qualifications and required a massive recurriculation exercise on a national scale. So at the moment we have six universities of technology, each of which offers between 200 and 300 programs, and almost every one of those was now no longer valid. It was a kind of an epistemicide of just killing off the entire knowledge base of the old technicons, and kind of forcing them to move away from that practice base, because nobody understood it. They didn't know what it was. And add to this the aspirations of academic staff linked to the new status of being a university, in very scary quotes. This is a recipe for academic drift. So, drawing on our understanding of semantics, we understand academic drift as an intention to delocate the qualification from its practice base along the prosaic worldly axis, and relocate them more towards the rhizomatic and rarefied zones. These are areas where they presumably have greater status, and that qualifications can then be rebranded. There might be a lot of name changing. I think we're quite good in South Africa at changing names, but not always good at understanding what these new names might mean. So I'm going to use an example from Shane Hollis-Turner was our first LCT doctoral graduate from our center, and her study was she subsequently published a couple of things on it. One of the articles called Rebranding Secretarial Training. So secretarial training sits very comfortably in the kind of prosaic zone, and it's based on the key field of practice of business communication, and this was what was taught, and it wasn't particularly high-level business communication. It was the kind of business communication which enables competence. Competence in terms of minute-taking for meetings and for running the lives, a kind of service-orientated business communication. And in many ways, when I kind of tell people that our university does have secretarial training, they seem quite shocked. Everyone, I must say, except the Scandinavian universities, where apparently they're okay with it. But it in some senses, a qualification like secretarial training perhaps should have been left behind in the TVET colleges, which are our equivalent of the TAFE colleges here. But it came along anyway, and as we have it, I think we need to do it well. So no one knew much about what secretaries do, except the secretaries themselves, and they didn't have much say about what went into the curriculum. And in the process of recurriculating the program to meet the requirements now of what is called the Higher Education Qualifications Sub-Framework, the qualification was given a new name, Office Management and Technology, because that's kind of, we're good at finding new names for things. And a collection of largely irrelevant subjects, such as mercantile law. And for those of you who were at Susan Hood's presentation yesterday, you must know that there is a vast world of difference between what secretaries do and what people in mercantile law and commercial law do. Things like financial accounting, again, perhaps a good thing for secretaries to do some basic bookkeeping, but to have these kinds of subjects put in, and quite a lot in the rarefied zone. These were put in, I think, in the hope that they might make the course more worthy of inclusion in a university. And the heart of the old curriculum, business communication. So that was where it was pulled to, and business communication was taken out. It wasn't taken out completely, but there was the business faculty, in its wisdom, decided that all the diplomas would have one communication module, so that one communication module would be shared between marketing, financial accounting, HR management, internal auditing, etc., each of which has got its own particular communication practices. And it was, for many of us who'd worked on Cecilia's project, it was a disaster, because we had developed resources and an understanding, together with the vocational lecturers, of what those communication practices were. And you must know, if any of you have ever been audited, either for a project or for other reasons, that auditors speak to you in a very, very different way to the ways in which secretaries communicate with you. So this is a disaster. I mean, they ripped the heart out of the secretarial training and replaced it with some dumbed down, pathetic course which floated off beyond the rarefied zone. And as a result, we now graduate highly unemployable secretaries. And unfortunately, many of our courses, although by no means all, and perhaps it was quite wrong of me to start with such a bad example, by no means all the courses followed a similar route. But a lot of them did, and this has caused, this is an extract from a presentation given by Professor van Staden, who's the chairperson of the South African Technology Network, which is based on the Australian Technology Network, quoted in the Higher Education World News last year at the conference. And he says there, he's calling for a stop to this academic drift and to revisit the institutional differentiation debate. He says we must go back to the Technicon days, but for me, I think the issue is not about going back to the Technicon days. It's about our failure now and then to understand the nature of the knowledge that underpins what we do. And what we do, according to van Staden, I've underlined that, is we train, I would prefer teach there, technicians and technologists, not engineers and not artisans. And it's the first time I've actually seen someone in a leadership position actually kind of say, this is what we do. So that's, we straddle this prosaic worldly continuum. And in retrospect, some academic drift was probably needed to strengthen the semantic density of the more technical programs, particularly those that tended towards the worldly plane. But as Sharon studies show, the inclusion of knowledge areas that are unrelated to the practice field are not helpful. So how might we distinguish between what is an appropriate scientific or theoretical base and what equates to academic drift in our programs? And I think the first principle that we draw from not only Sharon's study but from several studies is that the first principle of practical knowledge is relevance. Sharon's study brings this home, and it's a bit of a no-brainer. The knowledge areas selected for inclusion in a curriculum need to speak to the nature of the practice. Relevance is the main way in which knowledge that is described as high in semantic gravity relates to its context, and it makes practical knowledge domain specific, a lot more so, obviously, than theoretical knowledge. So, as I said, a little bit of academic drift is clearly not a bad thing, and the inclusion. This is one of the other studies. The inclusion of physics, for example, in some of the more technical programs. It always has been there, and its strengthening is quite a good thing. During 2012-2013, I had some funding for what we called the physics project, and we were looking at how physics is recontextualized across a number of programs for purposes of practice. So we first need to understand that this is the example that I'm taken is from Justice Bosman's master's study on physics in medical rescue. And you first need to kind of understand the logic of medical rescue, of the field, of where it is. So it's these young people who need to be very fit and very active, who race into all kinds of emergencies and rescue people off mountains and in the sea and in fires and you know, they are the paramedics. So the way in which they use physics is obviously going to be different from the way that the engineers use physics. But they can. What we found in Justice's project is that they can draw down into the qualification from physics. It should be obvious that physics is important to the work of medical rescuers, and is equally important that it shows in the curriculum. Both the practitioners and the academics are quite clear about this, and this is not academic drift. This is powerful knowledge for the field. So they have a very good physics teacher who, this is a part of their Physics 101 class, who are explaining to my colleague James Garraway, for those of you who know James, they're explaining the physics of some of their rescue equipment. And the principles of physics are obviously embedded in the equipment, and understanding the forces at work here are really is integral to their practice. What we found, and I'm not going to talk about all of the diplomas across the in the physics project, but we looked at the way in which physics, which is normally thought of as this ideal hierarchical knowledge structure, how it had been selected, excluded in some parts of it, and expanded in various diplomas. So most people who teach Physics 101 type courses will say that this is this in the grey area at the top, that's a kind of a traditional Physics 101, where you go from measurements to statics, dynamics, work, energy, power, solid and fluid, statics and dynamics, optics, electricity, heat and temperature, phase changes, and then perhaps some nuclear physics as well. But what we found, while the physicists were saying we've got to teach this whole range to everyone, the engineers are saying, and the medical people are also saying, no, actually you don't. We don't need it. We don't need it all. So we found that civil engineering, for example, focuses on statics and dynamics. Everybody does measurement, but they focus on statics and dynamics. Mechanical engineering takes that broad kind of spectrum of Newtonian physics. The electrical engineers hello, they do electricity. They don't do statics and dynamics of beams and bending moments in buildings. The chemical engineers tend to work in the phase change, heat, phase changes, etc. And the emergency rescue straddle quite a large area of the Newtonian spectrum, and the radiographers work very much in the nuclear domain, which is the stuff that the isotopes and stuff that they deal with, and they really don't need to know about levers and pulleys. For those of you who might have read David Layton's work, the Technology's Challenge to Science, he has this very nice metaphor, the cathedral and the quarry. So he says, for physicists, physics is a cathedral. It's something to be admired, and you make your small contribution, and you build there, and you go there to learn about this magnificent structure that is physics. For engineers, they see it as a quarry. What can I take? I might have a piece of this cornerstone and this flying buttress and this bit of stained glass would look good in what I need. And they don't worry about the rest of the structure. So what happens when they do that is an interesting thing. It changes the nature, it really changes the nature of the physics, and it makes the physics very, very useful to the engineers or the practitioners. For example, our electrical engineering technicians might work with a wider range of the understanding of electricity than the structural engineers. The structural engineers, their world, when they are planning the sort of power structures for a building, need to understand electricity as a current. They don't need to understand it as a cloud of charged atoms that travel along the copper wire, across nuclei, positive nuclei on a copper wire. They don't need that. It's way beyond. It's too surplus to their practice. And in the same way, when the civil engineers are working with insulation, a fairly simple understanding of heat transfer and a flow model of heat transfer is fine. It's just adequate. It's for what is required. So I could go on about this because there are some wonderful examples, and Nancy Cartwright's book called How the Laws of Physics Lie is a wonderful example of the ways in which how engineers are often flummoxed by the laws of physics, because science advances by simplification, and a lot of abstraction is simplification. It's taking the complexities of real life and situations, and making them more simple in order for science to advance. So in physics, beams of the kind that the structural engineers deal with are perfectly straight, and levers really bend or twist. Balls rolling down inclined planes are perfectly spherical and unhampered by air resistance or friction. And so decontextualization is a strategy for building scientific knowledge, but it's not particularly useful for practice. Engineers have to deal with the messy realities of the non-spherical and the slightly wonky beams, etc. So this is the kind of second principle of practical knowledge, that practical knowledge follows the logic of practice. It's about what works in a particular context. And as we've seen from the medical rescuers and the engineering technicians, theory is not absent. It is there, but it's there on a kind of a what you need basis. It's present in very specific ways. Practice, as Bourdieu explained it, it's not the logic of logic, it's the logic of practice. In other words, it's not necessarily the internal logic of physics, but it's the logic of the practice that tells you what is the physics you need for that practice. So in the world of solving these, of the technicians solving problems, they draw on this hybrid mixture of science and practical experience to explain, predict, and mathematically describe technological artifacts. Nancy Cartwright calls this the causal story that is told by technicians to each other, the causal story which helps them to draw on a range of different disciplines and modes of understanding. And she claims that what they're doing is they are not applying science to technology or applying science to practice. They are developing their own particular knowledge base. But because the knowledge base, of course, draws on physics, the knowledge base, practical knowledge, can have a lot of the characteristics of theoretical knowledge in the way that it's structured and logically organized. Giddens calls this, and it might have some, the sort of label of tacit knowledge is not entirely accurate or correct, because people can move from what Giddens calls practical consciousness to discursive consciousness. So they can describe what they're doing and describe what their understanding is. Okay, so we got quite interested, those of us working on this physics project, when it came to an end, we got quite interested in sort of following up what might be the consequences, because we know from that it's usually thought of as quite bad if you pull down from physics and you don't have the whole course and you don't understand it very holistically, you understand it for your own practice. So what might be the consequences of having this kind of practice, logic of practice directed physics in your qualification? What would be the consequences if you wanted to transfer to a, for example, professional engineering degree? So a group of us studied students, and there are many students who aspire to become professional engineers, but who perhaps didn't have the correct entry requirements to get into such a program where the maths and science demands are very high. But the University of Cape Town is perhaps unusual amongst traditional research intensive universities, in that they actually have a transfer program that supports the engineering technicians who want to transfer from a university of technology to the traditional engineering professions. So we had a look at several, I think about five cohorts, and at the University of Cape Town at any one time, approximately, I think somewhere around 10% of the student body in the engineering faculty will be transferees who came not only from our institution but from all universities of technology. So what we were interested in is to say that these guys, they're working at the technician level, they're drawing down on maths and physics all the time because they use that in their practice. They're moving across to traversing along the plane, they're wanting to take on the professional computer engineering, for example. Do they have enough maths and physics to enable that? And what we found was really interesting. Yes, they do have enough maths and science. In fact, the maths and science isn't the problem. Most of the transferees did as well, if not better than. In fact, in the basic sciences of maths and science, they outperformed the non-transfer, the mainstream students, and they did very well in the very difficult engineering sciences as well, like the digital systems, or if they were in chemistry, thermodynamics, etc. They did extremely well, but there was a problem, and what the problem was the design projects. their whole qualification had been around problem solving at a lower level. A bit of design was in their curriculum, but not much. And then they had to face the challenge of engineering design, which is very demanding. There's a lot of literature in engineering education which explains engineering design as one of the most challenging aspects of a deeply challenging course. And drilling down into what it was, there was an insufficient. You see, they'd pulled down from the maths and science, which helped them to solve problems, but they hadn't pulled down from the maths and science, which took them in another direction. It wasn't that they were not able to do that. That's what their course and their training was all around. It didn't mean that it was impossible for them. It meant that they unfortunately delayed their graduation because they tended to extend. Instead of spending 6 months on a project, they'd spend a year on a project because they needed to get that. But they were, I've simplified this case study a bit, but the point being that the maths and science, they could build on that, but the new area, it didn't travel so well. Earlier this year, I was at an engineering education conference in Athens and met a group who were doing something similar with transferees in the States. So it was a group from University of Indiana, Purdue, and they had funding to look at military technicians, people who served in the military and had been trained as technicians in the military, and they were then given opportunities to go to universities to become engineering professionals. And their findings were almost identical to ours. And they were amazed to find that their transferees were doing well in the maths and science and in the engineering disciplines, but came a bit unstuck in engineering design. So this is what I think another principle of practical knowledge is that it actually transfers quite well across similar contexts. So, we told the doctrine is that practical knowledge is restricted to the context in which it is developed and understood. And I think that's not entirely true. I think it travels well across similar contexts. So it can stretch, it can expand its range, and it does transfer the theory practice transfer, as long as the theory is relevant to the practice, does seem to work. However, it's very difficult to transfer practical knowledge across very different contexts, as we found with the trying to transfer it from technician level problem solving to high level engineering design. But it's not impossible. A lot of the students did complete. They didn't drop out. They did complete and finish their studies. So it's not impossible, but it is difficult. Because I think this has to do with, with Bernstein's notion of the reservoir and the repertoire. So what the maths and the science and the accumulative knowledge of the solving problems gets dumped into the reservoir, and that becomes the resource from which the technicians can pull a whole variety of reservoirs, of repertoires out of the hat. So that they certainly surprised us with the way in which they were able to, when we tracked them through the program. So I think the amount that you can travel across contexts is very much dependent on the reservoir. So the practical knowledge needs to be need to know, but it's usually surplus to need to know. So there's a wider range in the reservoir than what is strictly required for practice. Okay, another case study from Augustine, who's just started her master's. In fact, I think she's just completed her proposal. And this whole idea of the reservoir and the repertoire got us thinking as well about about how practical knowledge grows and changes over time. So what Augustine is doing is looking at tracking practice in dental technology. Now, dental technology is one of these qualifications which is usually thought of as terribly practical, so practical as to be, deeply sunk into semantic gravity, so much so that it can't really rise to the challenge of semantic density. But we think that this isn't entirely true. And what Augustine is doing is she's got her students developing portfolios over the course of their study. And in their portfolios, they take photographs of the prostheses that they fabricate, I think is the correct word to use. And they write about them, and they explain about their how they fabricated the prosthesis and the stages that they go through. So we thought it would. Penelope is the main supervisor. We thought it would be very interesting because we know that there's gravity there. A lot of it. We thought it would be interesting to see if we tracked semantic density across the portfolios to see how the density might be rising. So this is Augustine's translation device, in which she's used the revised Bloom's taxonomy and has linked that to aspects of the practice of dental technology. So they're kind of these eight levels of density, which we might reduce when the data comes through. So we don't have any results on this yet, but the gut feel is saying that perhaps there is this journey from novice towards expertise, with the density kind of climbing, or perhaps we see it in bubbles across students' practice as they get more and more proficient. So from other studies as well, we think that practical knowledge is cumulative. It's the kind of knowledge that grows layer by layer, the sort of knowledge that you have to practice in the same way that jazz musicians have to practice to get to the level of expertise that was demonstrated on Monday night. So anyone involved in practice has to practice. And it is through the practice that the knowledge base accumulates and continues to be built. Okay, I think there's time for a final case study, which we've called an exemplary diploma. A couple of years ago, a group of us got funding across the University of Technology sector to look at graduate attributes, which are normally these fuzzy, nice-to-have things which people put onto their curricula but really don't know what it is. And we selected 6 flagship or good programs across the University of Technology sector and tried to reverse engineer them to see what were the underlying mechanisms which made possible their equivalent graduate attributes, such as employability is one, ethical practitioners is another, entrepreneurial outcomes, that kind of thing. So just a quick example from one of the diplomas that was chosen, which is the Diploma in Biodiversity and Nature Conservation. These are the people that become game rangers, and they trained in these fields of basic sciences, zoology, botany, soil science, ecology, and so on. Also, this was the first time we found in a diploma program stuff in the rarefied zone, conservation communication, which is really important in the South African context, where conservation practices have tended to exclude many communities. It is vitally important that the people working to conserve the biodiversity of the region, communicate with communities and involve communities in the practice of nature conservation. The students and the staff in this program are very fortunate to have a really good head of department who is Kenyan, who worked in the game parks of Kenya and who has a passion for nature conservation. And achieving a graduate attribute like ethical practitioner is not an easy ask. It affects the internal structure of everything that you are trying to do. And it comes from practice. This is what our study of these 6 flagship diplomas are telling us, that while it pulls down its relevant mix of subjects to enhance practice, it's really through practice and field work in particular, kind of the sustained engagement with practice that helps the students to develop their values as nature conservationists, both to protect the biodiversity of their particular corner of the planet and to engage with communities in order to ensure that the communities benefit to some extent from nature conservation work. So field work and working with communities is key to the students developing their identities as the custodians of biodiversity, and practice is the key curricular element. Its ethics is developed through their practice, and I could only imagine that it would be almost impossible for the game rangers to develop that passion for nature and conservation if it wasn't for their field work and their work with farmers. They do a lot of work in conservation of for example, the Cape leopard, and work with farmers to prevent the farmers from shooting them, to suggest alternative means of protecting sheep from the Cape leopard. And so they develop this kind of deep sense of who they are and an ethical core to their practice. And because time is running out, I'm going to use the same diploma to say a final principle for practical knowledge is that it's innovative. It's only through dealing with the practical problems that innovation tends to happen. Innovation, I think it's again Leighton who says innovation could be understood as an attempt to create a new culture that places a high value on practical capability. So many of you probably know that our rhinos are very endangered. If you go to visit a game park in South Africa, each rhino has its own armed guard to protect it from poachers. And we're fortunate enough to be able to place our students, because we work a lot with the World Wildlife Fund, to place our students in some of the big game parks, and they worked with the World Wildlife Fund to figure out ways of protecting the rhinos beyond each one having an armed guard. And someone in the course of practice came up with a bright idea of why not take the rhinos to a place of safety, and the government of Botswana agreed to host all of our South African rhinos until such time as the poaching problem could be sorted out. So here we call this project the Flying Rhinos Project, and the students have been learning how to fly rhinos, and I think it's helped them to think very creatively and innovatively about their practice, and particularly in following up the work of the conservation of the rhinos. Okay, so I'm going to try and bring everything to a close. So to summarize, practical knowledge is really something quite different from theoretical knowledge. It's relevant. It has greater relevance to its context. It's cumulative. Is transferable within certain limits. Logical, with the logic of practice, not the logic of logic. It's ethical, or ethics develops from deep engagements with practice and can be very innovative. Leighton calls science and technology, and I can translate that perhaps to theoretical knowledge and practical knowledge, mirror image twins. So I don't think they're quite mirror image twins, but they are related, and they can pull across each other. They can draw some of the applied disciplines clearly pull from the field of practice. Practice pulls from the disciplines. And you don't lose your ability to conceptualize just because you are in your practitioner mode. And like theoretical knowledge, practical knowledge meets various standards of coherence, but its primary function is not to objectively verify, analyze, generalize, predict it, etc. Its prime function is to guide practice. So, linking the two domains is, of course, context. And context can be simple or complex. And they can be artificially controlled, as in a laboratory, or they can be allowed to intrude in all their complexity. Thus, material contexts can be minimal or dense, with what Knorr-Cetina calls epistemic objects that require high levels of intellectual engagement with practice. And the sociocultural context is always present in communities of scientists, professionals, practitioners who have set the particular rules of engagement. And there are historical contexts, traditions, and historical practices that exist in layers, whether it's in the form of the existing code that computer engineers draw on, or long established protocols for the treatment of particular diseases. And this is something that I know that my colleague Penelope and others get quite upset about. How on earth can a protocol to avoid needle stick injury in hospitals be devoid of any conceptual knowledge? It's based on the most up-to-date understanding of the HIV virus and how it is transmitted. It's a protocol, but it's a conceptually based and scientifically appropriate protocol. So there are ethical considerations and choices to be made, and the problem context is a particular important one for practitioners, and can be an incredibly complex context. And it's a context from which innovation can emerge, and new sets and benchmarks for practice can emerge. So, I think when you look at it a little more closely, as we've tried to do using the LCT tools, we can see that practical knowledge is neither subsumed by or completely outside of theoretical knowledge. Communities of theorists and practitioners constitute interdependent, parallel, and epistemologically equivalent bodies. But if we assume that practical knowledge is knowledge, then its study is warranted, and it warrants a scholarly effort parallel to the attention paid to theoretical knowledge by philosophers, historians, and social scientists. And I believe that the studies of our Wilry researchers and others in the field that are being undertaken with the tools provided by LCT are yielding powerful and rich ways of describing and analyzing the knowledge resources of this particular field. I think LCT has really helped us to kind of move beyond the binaries and to see the practical knowledge in all its complexities. And I thought you might have noticed that my representations of knowledge landscapes becoming more abstract. So this slide represents the warped time-space, and it represents the effect of semantic gravity on theoretical and practical knowledge. Semantic gravity can enable abstraction as it weakens, and as it strengthens, it can enable a focus on real-world problems and specialized knowledge fields. And sometimes it does both together. And LCT has made visible to ourselves as educational researchers and teachers the structuring principles that underpin professional, vocational, and technical programs. Semantics has helped us to analyze the relationship between knowledge types and to show how they are represented in curricula. And I must point out to you that I've only shared with you one LCT tool, and there are studies that our group are undertaking using many of the other LCT dimensions, and I look forward to hearing some of the presentations on these and sharing more work with you in the future. Thank you.